All right, so in terms of our calendar, we have a test scheduled for next Tuesday. Y'all okay? We push that back one day or 2 days? All right. If we push it to the 21st?
Sure.
All right, so that's officially, we're going to move the test. That way we can talk a little bit more about it on Tuesday, and we'll talk maybe a little bit about what to expect today. We're not behind or anything. That kind of crept up on me. I didn't realize it was that soon. So today's the 14th. Yep. Well, we're still going to cover material, but all right. So let's get going here. Everyone's turned in their take-home quiz. All right. Yeah, there's a lot of people missing. Quiz wasn't that bad, was it?
They're all still in the math lab.
They're all still in the math lab, right? All right, let's get going. All right, today is a very important day, all right, for what we're going to talk about. 7.5, the unit circle. And specifically the trig functions. Now, how many of you have heard of the unit circle before? Yeah? Okay. So a circle that is centered at the origin, that has a length of radius of 1. Okay, so that's 1 unit, is called a unit circle. And unit standing for 1, all right? The unit circle. It is centered, like I said, at the origin. So the equation of this circle is x squared plus y squared equals 1. That is the equation for that circle. All points that lie on that circle must satisfy that equation. So if you pick some random point here, its x and y coordinate must satisfy that equation. Now, what we're going to do today is we're going to take our idea of the trig functions that we've developed, and we're going to actually kind of reevaluate them. And from here on out, this is going to be probably the main thing you turn to when it comes to trying to figure out, like, what's sine of 30 degrees? What's sine of 7 pi over 4? You want to understand it based off the unit circle. When I'm in a Calculus 1 class or Calculus 2 class, and I get a student who doesn't remember what sine of 30 is, I don't go and reteach them all Chapter 7 in pre-cal. I take them back to the unit circle, and that's where we base everything from. So if you understand this, you'll be in good shape, all right? But let's see how we're going to use what we've learned and somehow map it over to this idea of the unit circle. So if I draw from last class, if I pick some arbitrary point, okay, now this point's completely arbitrary, all right? It's not sitting on a circle or anything. And I call that xy, right? And then what we did last class is we said, well, if we could measure the distance from the origin to that point, call it r, then we could define our trig functions. Sine theta, theta is this angle. We said sine theta is y over r, thank you. Cosine theta is x over r. And tangent theta is y over x. And then the other 3 functions are just the reciprocals of those, right? Now that r, like I said, is arbitrary. It doesn't have to be any specific number. So what I'm going to do now is I'm going to come in here. And I'm going to draw in here the unit circle. So I'm going to just stick the unit circle onto this picture. I'm not sure where 1 unit is, all right? That could be, 400, so the unit circle would be really small, or that could be 2, where the unit circle would be somewhere in here. So I'm just going to just throw the unit circle in there arbitrarily. I'll put it about right here. All right, so let's just say, for the sake of demonstration here, that now I have fixed that to be 1, all right? Now with this picture in here, if we look at, I want you to look at 2 different triangles. I want you to look at the triangle that's formed by dropping straight down here. See that right triangle there? And I also want you to look at the triangle that I get by taking where this line hits the unit circle and dropping down like this. Okay? Do y'all see the 2 triangles? All right, now I'm going to draw those 2 triangles over here now. We have, I guess, a bigger triangle and a smaller triangle, right? Okay, so I'll draw the bigger one first. The bigger one here. This is R, this is Y, this is X. Do you agree? And theta's in here, sorry. Like that. That's our bigger triangle. Because this side is X, this side is Y, because that's how we get to that point. Now I'm going to draw the smaller triangle. The angle here is still theta, isn't it? Yes. Okay. Now, do you know any of those sides?
Yeah.
Which one?
R. Yeah, R.
This right here? It's 1 now, right? Because remember, I drew this blue circle to be unit circle. So this side from here to here is 1. Now, is this side X? I'm sorry, is this side X? No. Is this side Y? No, it's not, right? But let's label it something, all right? I want to label it something even though it's not this X and not this Y. And I'm just going to, we could call it A and B. Y'all want to do A and B? We can do that. A and B. Now, is there something about these triangles that we can say, I mean, they're not just like random triangles. They're somehow related to each other. We call them what triangles? If they have the same angles, because they all have the same angles, don't they? They both have a 90. They both have theta, which means whatever this angle is here is the same as this angle here, right? So when you have two triangles that have the exact same angles in them but are different sizes, what do we call those triangles? You know what they're called? No.
Equilateral?
No. That's all sides. Similar? Have y'all heard that before? These are similar triangles. And we're using the word similar here, not like, yeah, you know, similar, they look kind of the same. I mean, similar is more precise. Similar means that we have a very, very special relationship between the sides of the triangles. And that is the ratio of the sides are congruent. What? Well, here's what that means. It means if I take the side that is opposite of this angle theta and divide it by r, that ratio, it is the same as the ratio of this side, this angle opposite over this side. So that should be equal to what? B over 1, which is just b, right? Understand? And then if I take any other ratio, like if I take x over r should be the same as a over 1, which is just a. And if I take, let's say, y over x, that ratio should be the same as b over a. And I could do this for any ratio I want. Similar triangles allows you to say this, all right? So with that in mind, I want to now start with the trig, develop these trig functions again without this, well, using this picture, but just focusing on the unit circle. Okay? Do you recognize from this picture where B is and where A is on that picture?
A is X and B is Y.
A is the X coordinate of the smaller triangle. So you see this point right here? That has the coordinates A, B, doesn't it?
Cosine T is
Right? That's what this point, this is A and this is B, right? So that has these coordinates, this point. Okay. I want to kind of leave that up there. Maybe I can leave, what can I get rid of? Maybe this. Here we go. All right, so we're going to keep all that kind of on the back burner now, and now I'm going to draw you a unit circle. All right? So if I draw a unit circle, the only way I need to do anything to let you know it's a unit circle is just by putting a 1 right here at that point so that you know that now it's a unit circle. If I pick some angle in here and pick some point on this unit circle, and I'll stick with AB for right now, but I'm going to have to switch it in just a second, and I say this is theta, then what's sine of theta? What's sine of theta? What's cosine of theta? And what is tangent of theta? Sine of theta is B, right? Because it should be the sine should be the y coordinate divided by the radius, right? But we already said that because those were similar triangles, that should just be B.
Cosine of theta will be A.
Cosine of theta will be A, and tangent of theta is B over A. Now, it may not seem like we've done anything here, and I get that, but here's the way I want you to interpret this. If you're looking at a unit circle, okay? So if you're looking at this, then isn't this really saying to you that sine of theta is just the what? What is this? In terms of that point, what is that? B is just the y coordinate, isn't it?
It's like the A and B point, a real number point.
It's the y coordinate. Of the point. See, no ratio, you don't have to worry about opposite over hypotenuse because the hypotenuse is 1, right? So the opposite side divided by 1 is just the opposite side. So sine of theta should just be the y coordinate of the point. Cosine of theta would be what?
1 over B.
A over B. Remember, this is A. A over 1. Cosine of theta is your x divided by your r, right? Which is just A for us. Because remember, this is A, that's B, that's 1. So cosine of theta is just the x coordinate of the point. And then finally, tangent would be what? The y coordinate divided by the x coordinate? This only works if you're on a unit circle. If you're on the unit circle, then the actual x and y values tell you exactly the value of the trig function. Do you get that? These numbers are the answer to the question of what's sine of the angle. All right, now, this is the idea I used A and B because I had drawn the other triangle with radius r. So what I want us to do now is kind of wipe the slate clean and start over with a new picture, and then we can use x and y again. Because I want to use x and y because that's what the book uses. I don't want to use A and B. But just remember that. Sine of the angle is the y coordinate, cosine is the x coordinate. All right. Unit circle. One. We pick an arbitrary point on the unit circle. We call that point x and y, x comma y. That forms an angle right here. We are going to call that angle T. Why? Because the book wants us to call it T for right now. And I'll illustrate in the next section next week why we're going to use T, but it's really kind of a dummy variable. We could have used theta, but I'm going to use T. So what is sine of T? What is cosine of T? What is tangent of T? Sine of T is what? Which is the y coordinate, right? Which is y. Cosine of T is x, and then tangent of T is y over x. Okay, good. So if somebody hands you a unit circle and asks you for sine, cosine, or tangent of some angle that they give you, you're just going to need to know the x and y coordinates of the point that they're talking about, right? If you have those, then you're in business. So that leads to the next natural question, I think, which would be, if you take the unit circle, what are some points you know on this circle already? Like what are...
1, 0.
Okay, this point right here, which is the point 1, 0. I know this one, right? 0, 1. I know this one, negative 1, 0. And I know this one, which is 0, negative 1. Right? What's that? But it's not on the unit circle, right? So we want it on the circle. Okay, you ready? Quiz time. Not quiz for real, just quiz time, like thinking. Make sure you turn in your take-home quiz if you have it. What is cosine of pi? No calculator. So no one giving the answer yet. But if you have the answer, raise your hand. What is cosine of pi? Okay, so what is it that you are doing to get the answer that you're about to tell me? Try to.
Well, I go back to like where we get like, yeah, 180.
Okay, so you're saying pi is 180.
Yeah.
So you're going to 180 degrees on that circle, and then what are you going to give me?
The exponent,
Yx,
because it's cosine.
because I said cosine. Right? That's exactly what's being done. When you say what is cosine of pi, right? What you need to do is you need to see that pi is 180 degrees. So you're like rotating through here. You're at this point. And since you're saying cosine, you're picking off the x coordinate. So cosine of pi is negative 1. I was sitting down today with a mind, like a mental image of the unit circle. That's the way I do it. You know, just close your eyes and see 180 and see the point and pick the x coordinate off. Right? That's the way you should do it. It should never be pull out the calculator. That means you didn't really ever learn it. You just become dependent on that calculator to make it make sense. What's sine of pi?
0.
Sine of pi is 0. The only difference between those two is that now I'm picking off the y-coordinate, right? Okay. How about cosine of 3 pi over 2? So you got to know where that is, right? So 3 pi over 2, you're going to count by pi over 2's. So pi over 2 is 90 degrees, right? So I'm going to count 3 of these. 1, 2, 3. And I'm picking off the x-coordinate. 0, right? What is sine of negative 3 pi over 2? Negative 3 pi over 2 means I'm going to do a clockwise rotation, right? By pi over 2's, I'm going to need 3 of them. 1, 2, 3. Okay, it's that point, and I'm picking off the y-coordinates, 1. You'll see how this works? All right, let's do another one. How about tangent of 0? Now, I didn't put 0 degrees or 0 radians, did I, right? So if there's no symbol here, it means radians, right? But 0 degrees and 0 radians are exactly the same, aren't they? Okay, so you're raising your hand. What do you got?
Just 0.
Okay, 0. Why is it 0?
Because 0 over 1 is just 0.
Why are you doing 0 over 1?
Because it's tangent is y over x.
That's right. Tangent, by the definition, is the y-coordinate divided by the x-coordinate. So when I go out to 0 degrees, that's right here, I'm going to take the y-coordinate and divide it by the x. 0 over 1 is 0. Everyone clear on that? All right. Any questions? The looks on your faces is like either this is too easy or you're like way out there somewhere. Yes?
How did you know to look at that coordinate for tangent?
To this one, what's the angle? What's this angle? The angle is 0, right? So remember, this is 0 degrees, right? And then, okay. Any other questions? Ask obvious questions if you've got them. I mean, trust me.
What about the cosecant and secant?
Yeah, let's do those. That's where I was about to ask you what tangent of pi over 2 was. So you should be first figuring out where pi over 2 is. Then you should be trying to take your y-coordinate and divide it by your x-coordinate. And you should be having a problem with that, right? You're getting 1 over 0. This is undefined. Tangent of pi over 2 is undefined. You're trying to divide by 0. We're not allowed to. All right? How about secant of... How about secant of pi? What's the definition of secant? 1 over cosine? So this is the same as 1 over cosine of pi, isn't it? Cosine of pi, you're going to rotate through pi and grab your x-coordinate because it's cosine. The x-coordinate at pi is -1, isn't it? So this is going to be 1 over -1, which is -1. What is cosecant of pi? Undefined. Because now you're trying to do 1 over sine of pi. And sine of pi, 0 is the y-coordinate, right? So undefined. what is sine of 33 pi over 6? Oh, wait, hold on. We're not there yet. Pardon me. I jumped a little too far ahead there. What's sine of 33 pi? We'll just do that. Should be 0. Now, you could count your way around, couldn't you? Pi, we have 33 pi's, right? So pi is this, right? I could do that 33 times. I could go 1 pi, 2 pi, 3 pi, 4 pi. But what I'd start to notice is that every time I land over here, I'm at an even number, right? So this is either 0, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So I've got all my evens over here. My odds are over here. So 33 pi should be at this point, shouldn't it? And I'm looking for the y coordinate, which was 0. Well, life would be good if that's the only stuff we would need to know off the unit circle. But there's more angles on there that we should probably know, right? And do you remember when we were learning the common angles? All right, so let's go with the next group of angles that we should know. And it's the 45-degree angles. And these are, what, pi over 4? Or you could say 45 degrees. Yes? Now, the question becomes, what is the point that corresponds to that angle? What's the x and y? It would almost be half-half. Here's how we would get it, and we developed this, we did this a while back. If this is 45 degrees and this is 1, then these two have to be the same length. And what we realize is that that means it would have to be square root of 2 over 2. So I won't go through that again, but this has as its point root 2 over 2, root 2 over 2. And you need to just remember that for 45 degrees. All right. Now there's more, right? But let me ask you a few questions before I move on to the next, to a couple of different angles. What is sine of pi over 4? So you're rotating through pi over 4, and you're grabbing off that y coordinate, which happens to be the same as the x coordinate. But cosine will be exactly the same, right? Cosine of pi over 4 is also root 2 over 2. And what about tangent of pi over 4? It's 1. Because when you take the y coordinate and divide it by the x coordinate, they're the same numbers, right? Root 2 over 2 divided by root 2 over 2, that should give you 1. Okay. Now, I know some of you in the past have been taught that you should memorize the unit circle. I'm not a big memorizer, okay? Now, I do have this memorized now, but it took many years for me to memorize it. My suggestion is to not think of the unit circle in terms of this big circle you have to remember. Only think of it as you need to remember the first quadrant, okay? If you can remember the first quadrant, this one, then everything else is going to flow very naturally from the first quadrant. And I'll show you how that would work. Let me ask you the question. If you know the answer, just hold on to the answer for now. But I want to know how comfortable you feel with this. Sine of 3 pi over 4. And then cosine of 3 pi over 4. All right, so you have to think, where is 3 pi over 4, right? So are we all looking at the same place here? Let me grab this marker. We're all over here, right? That's what I'm talking about? So we would need to know what the x and the y coordinates are, right? What are they? Negative root 2 over 2 and root 2. Why is it negative root 2 over 2 and root 2 over 2? So there's symmetry here. What you need to see is the symmetry. If I take this point and I reflect it over the y-axis, right? Then do you agree that the y values, how high up you are, doesn't change, right? So my y value is exactly the same as it is here. Now the x value, this distance, it's the same distance, but it's now this way, so it's negative. So my x coordinate has to change to negative root 2 over 2. Understand that? So what is sine of 3 pi over 4 then? It's the y coordinate, right? So root 2 over 2. And then cosine is negative root 2 over 2 because it's the x coordinate. You know when we write ordered pairs, it's always the x before the y? The way that I remember which is the fact that c comes before s in the alphabet. Cosine comes before sine, right? So I always remember the x, this is the x, and that's the y. If that works for you, great. If it doesn't, figure out your own way. All right? What is tangent of 3 pi over 4? Negative 1. Because now when you take the ratio, same numbers, opposite signs, you're going to get negative 1. All right. Let's see if we can fill out the rest of the points now for the 45-degree angles using the same idea of the symmetry. How about this point down here? They're both negatives, right? So the only thing that changes is that to get from here down, the x-coordinate stays the same, but the y value now becomes a negative y value. So negative root 2 over 2, negative root 2 over 2. And then this one over here,
Sin will be positive and cosine.
positive for the x-coordinate and negative for the y-coordinate. All right? Positive x-coordinate, negative y-coordinate. All right, so now we have a whole other group of things that we can ask, like, all right, maybe I can ask this one now. What is sine of 33 pi over 4? Root 2 over 2, negative root 2 over 2. I've heard two different things. Got to figure out where we are, right? Got to figure out where you are. So how would you like to figure out where you are?
Double the denominator, double the denominator, and then divide that by 33, then the remainder is how many times you go around by the original denominator.
Double the denominator?
Yeah, make that 8, 33 divided by 8, you get a remainder of 1, and then you only have to go 1 pi over 4.
Yeah, he's saying divide 4 into 33, take the remainder.
Oh, divide.
No, you double the denominator.
Why?
Because 1 pi is only half a rotation, so you make it a full rotation.
Oh, you're trying to find how many full rotations. Got you. Okay.
Double the denominator, then you divide that. 33 divided by 8 is a remainder of 1, so then you only have 1 pi over 4.
Okay.
That's the easiest way for me to figure it out, so you know exactly how many rotations.
And I think if you can figure it out that way, that's the way you do it. So you have two options. You can actually march around 33 increments of pi over 4, or you can figure out how many full rotations can you get into this, all right? In other words, how many times does 2 pi go into this? And then how much would be left over? So that's what you were saying. When you divide by 2 pi, that's what you're doing. Dividing by 2 pi is doubling the denominator to 8. Now, the way I showed in class before, right, the way I showed was I said take 33 and divide it by 4. How many times is that? How many times does 4 go into there? 8 with some change, right? 8 with some change. So what we can do is we can take 33 pi over 4, and we can subtract from it 8 pi. You all okay with that? And let's see how much we would have left over. Because wouldn't 8 pi, this would be 2 pi, 4 pi, 6 pi, 8 pi. That's how many rotations we've gone. But then what else? And so that's what this is going to get us. This is going to get us the difference, what's left over. So this is where you would need a common denominator. Multiply top and bottom here by 4. So 32 pi over 4. Understand? And subtract, what are you left with? just pi, right? 33 pi's minus 32 pi's is just 1 pi and then over 4. So what you're going to do is you're going to go around 8 pi, which is 4 rotations, and then another pi over 4. There's different ways to get this number. I mean, it's really multiple ways. Sometimes, I would say sometimes you just count it out. Shit, if we would have counted, we would have already been done, right? 33? Okay. But we're all going to be okay with the fact that we're here. That's where we are. And what is sine of 33 pi over 4? It's the y coordinate, so root 2 over 2. All right. Let's do the next common group of angles. Now, it starts to get kind of cluttered, right? So I'm going to start with the new circle so that it's not cluttered up on there. And these are the last common angles we need to know. And they are the 30-degree angles, which is the same as pi over 6, right? These points will still be here, because we do hit these points when we start marching around by 30 degrees. So we've got one here, we've got one here, then straight up, and then over here, 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 oops, I missed, and here. There they are. Now I said that the most important thing for you to remember is the first quadrant, right? Did y'all see how by us knowing this first quadrant, I got these other points by just reflecting over and just thinking about what the signs had to be? Okay, for this we're going to do something similar, but we're actually going to have 2 different groups of answers that we have to remember. So this is 1, 0. This point and this point, I did prove these to you a while back, what these were, but it's root 3 over 2 and 1/2, okay? But the question always becomes for students, which one goes where? Like, I know that it's root 3 over 2 and 1/2, but I'm not sure is it, which one goes first. So
Root 3 over 2 is first, is the cosine. Here's
this one right here and this one here, and then it's backwards up here?
Yep.
Okay, how are you going to remember that?
Half is smaller,
Half is smaller?
so you don't go up as much for the y.
So yeah, compare these 2 numbers, right? Compare these 2 numbers. Do root 3 over 2 and compare it to 1/2. And ask yourself which is bigger, right? So why don't we do this? Let's just guess that that's bigger than this. Let's see if that's true. Well, multiply both sides by 2. And wouldn't you get root 3 is bigger than 1? Right? If I multiply both sides by 2, is this right?
Yes.
This is right, right? I'm making a guess here. I think this is bigger than this. All right? I multiply both sides by 2. Is this true?
Yes.
The square root of 3 is bigger than 1, isn't it?
Yes.
It's bigger than 1?
Yes.
Okay. So this is a true statement. Now, why is that valuable to me? If I'm going to go out to this point, what has to be bigger? My x-coordinate or my y-coordinate? My x-coordinate has to be bigger, doesn't it? Which means this is the one that goes for the x. So you have to remember that the root 3 over 2 is bigger than 1/2. And then that helps you remember I go out further than I go up. So the root 3 over 2 is here and the 1/2 is here. Now if you look at this one, you don't go out as much as you go up, right? You only go out this much, you go up that much. So the root 3 over 2 has to be the y-coordinate. All right? Understand that? Okay. This is pi over 6. This is 2 pi over 6, which is the same as pi over 3. And then the rest of them, well, we have ways of counting our way around. But let's try and label these points. What would this point be?
It's negative 1/2.
Negative 1/2 root 3 over 2. So you are actually just reflecting this point straight over, aren't you?
Yep.
Okay. Now, let's reflect that point straight down. This would be negative 1/2, negative root 3 over 2. right? So the only thing that changed is the y coordinate became negative, so it flipped it over here. Now take that one straight across. 1/2 negative root 3 over 2. And that's it. I could take it back up, but I'd be back where I was. So you see how I use this one value to pick off these other 3? Now I'm going to take this one and reflect, reflect, reflect. So when I reflect this one over, what's the, thank you, what's the x coordinate and y coordinate over there? So negative root 3 over 2 and positive 1/2. Reflect it down, which puts you here. They're both negative. And then reflect it over here, positive, negative. I'm going to ask you some questions about, values of these, but I'm going to just kind of recap right here by just drawing my first quadrant. So my argument is that if you can remember these, then all the others are just going to be reflections. And so you just have to make sure you get the signs right on those. That will take some time, all right, for you to get that. Do y'all mind getting the door? Thank you. What is sine of 150 degrees? I already know I'm looking for the y coordinate, right? Y coordinate? I just need to know the angle. So 150, however your brain wants to do this, if I were doing this, I would say 150 is 30 less than 180. So I would be like, okay, I'm here, but I got to go back up that much, right? The y coordinate is 1/2. So 1/2. Notice that to get that, though, I'm actually looking at this, right? Actually looking at this circle. You want to get to a point at, maybe not, it may not happen here like right away, but maybe by the end of the semester where you don't need to look at anything, that you can actually see that angle and see the circle. All right, how about cosine of negative 11 pi over 6? So our rotation here is clockwise, right?
Negative root 3 over 2.
Clockwise by, I'm counting by pi over 6s, right? Pi over 6 is 30 degrees. Counting 11 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right?
Yeah, it's root 3 over 2.
Root 3 over 2, the x coordinate.
That's where your little square and or doubling the denominator works pretty good.
Yeah, you could also say, hey, that's almost 12 pi over 6, right? What's 12 pi over 6? 2 pi? So it's like I'm going to go around clockwise because it's negative 2 pi, but then I need to come back by pi over 6.
Yeah.
So that it's just,
Remainder right away.
exactly. It's really kind of up to you how you do it. What you don't want to do is be sitting in a Cal 3 class and someone asks you what cosine of pi is and you break your calculator out. That's what you don't want. How about tangent of 4 pi over 3? where is 4 pi over 3? Remember, this is pi over 3, right? 2 pi over 3 is right here. 3 pi over 3 is right here, right? And 4 pi over 3 is here. Are y'all having trouble finding 4 pi over 3?
1, 2, 3. Oh, yeah.
Root 3 over 2 divided by half.
So this is 1 pi over 3. That's 60 degrees, right? Add another 60, you're going to be at 120, right? Wait, 63 pi. Oh, we're 4 pi over 3, sorry. Add another, I went too far here. So 60 degrees, another 60, and you'll be at 180, right? And then you'll be another 60, you'll be right here. Tangent is the y coordinate divided by the x coordinate. So I'm going to take negative root 3 over 2 and divide it by negative 1/2. Negative over negative is positive. So this is really root 3 over 2 times the reciprocal, so 2 over 1. The 2's cancel and you just get root 3. Turning division into multiplication of the reciprocal. Y'all comfortable with this so far? Okay. Do you feel as if I gave you a unit circle that you would be able to do this? Like if you had a unit circle? Yes? Okay. On the first exam, I will provide you a unit circle. We'll try and wean ourselves off of it, though. All right, let's try something else. How about tangent of 330 degrees? So that's almost 360, right? It's almost all the way around, but you have to come back 30 degrees, so it'll be right here, won't it? And I'm taking the y coordinate and dividing by the x, so negative 1/2 over root 3 over 2. So similar to this, but they're flipped over, and then one of them's negative, one's not. So my answer should be negative, right? Negative 1/2, and I'm going to multiply by the reciprocal, so 2 over root 3. Cancel, cancel. So I get negative 1 over root 3, right? Which is an answer that I would be okay with on a test, but the book would not leave it like that. They would put negative root 3 over 3. So they would rationalize the top and the bottom. And that's actually important to recognize this, because later on what we're going to be doing is talking about inverse trig functions. And inverse trig functions do the reverse process. So it's like, you know how right now we fed into the function 330 degrees and it spit out this number? Later on we're going to feed it that number, it's going to spit out this angle. So you need to recognize this number as it's one of the common answers you should get. All right.
There's a lot of homework.
Pardon me?
Quite a few of those.
Yeah, there's a lot. Oh, by the way, I was not able to get the homework solutions done today. I had a lot of students come in for help today, so didn't get to it. I'll try tomorrow, but I have another lot of students coming out. I'm giving a Cal 3 take-home exam, and it's due on Monday, and they've had 2 weeks, but they all want to come get help
The last minute.
the last day before. I don't know. I've never heard of that happening before. I'm kidding. Yeah. Yeah, that always happens.
So the exam's moved up to next Thursday?
Yes, if you came in a little late, the exam that is scheduled for Tuesday is moved to next Thursday, the 21st.
Is that behind, or is it just better?
We're not behind. It's that I honestly just was not ready for that exam to give it. Like, I like to spend that day before talking about it, and I haven't really thought about it yet. So
So this is the last section today, it's going to be for the exam?
no, that's not necessarily the case. Yeah, there will be something from next Tuesday on the exam. I just won't hit heavy on it. It'll be kind of on the lighter end of what we cover. because I know you'll only have like 48 hours or so to absorb it.
But then we'll have time to do a test review.
We won't, yeah, I'll say right now, don't expect a handout test review, okay?
Yeah, but it's in class review.
Don't expect us to take time to like go over, yeah, I mean, at this point, we are at a point, I know y'all don't like this, okay? But we're at a point where your review is going to be, you better have been doing your homework and doing well on that and following through, and I will promise to stay within the scope of what was asked in the homework and anything that I presented to you in class or on a quiz. That is what you should be preparing for. So part of being a good student is knowing how to study for an exam without being given some guide. And it's just because y'all are growing up. No, y'all are getting old, you're getting further along in college, and at some point you stop being spoon-fed what the exam's going to be. All right? So you go study. You study your homework. All right? Now what I might do is say, hey, look, I like these problems. That'll probably be what the review is like. It'll be 10 minutes of me flipping through pages going, yeah, that problem looks really good. I would look something like this, Those aren't so much, something you should focus on. So I'll kind of narrow the field a little bit, but I'm not going to give you something where it's like, here's 10 problems, be able to do these. Sorry. Okay. We need to start talking about some of the properties of these trig functions. We've developed the idea that off of a unit circle we can find the trig values of common angles, but now we want to start looking at the trig functions like functions. And what we mean by that is, like when we talked about functions in college algebra, functions, basically a rule that assigns a value that assigns exactly one value to an input. This is a very loose definition of a function. It's a rule that assigns exactly one value to an input. And we have like this classic picture. I don't know if you've ever seen something like this where you have like, you got input, this is like a little machine, and then it spits out output like this, right? And our input right here, this is the function, and then the output. Normally, what we deal with in classes like this are functions that take in numbers, right? Take in numbers, spits out numbers. So numbers goes through the function, gets transformed somehow, you get another number out here, right? Number to number. There are functions that don't do that. There are functions that take in numbers and spit out things that aren't numbers, all right? But for us, this is what we look at right now. Classic examples, f of x is x squared, right? Input, output. Example, f of x equals x squared. I know this is going to seem very childish, but hopefully you'll see where we're going with this. For this function, f of x is x squared, the input here we call the x, right? And the output is the f of x. It's the function's value at x. So let's throw a couple of inputs into that function. 0. Okay, we can plug in 0, it's going to spit out 0. We plug in 1, it spits out 1. We plug in 2, spits out 4, 3, 9, so on and so forth. Now, can you plug negative numbers into this function?
Yes.
Yes. Negative 1 goes in, you get 1. You plug in negative 2, you get 4, right? So that's a function. What we want to do now is we want to start looking at these trig things as functions. They have inputs and outputs, right? So let's start with the sine. Oh, what's the domain of this function? I should talk about that before I move to sine. What's the domain of this function right here? Domain. Now, when I say domain, what do I mean by domain?
Where it is in accordance to the x-axis.
You're thinking about it geometrically. It's the x-axis. That's okay, but more from the perspective of the machine. What is the domain of a function? If I give you a function, I say, hey, what is its domain? What am I talking about? Not the output. It's what can you put into the machine? The domain is what you're allowed to plug into the machine. Right? You're thinking of the output that's the range.
The area which it could be inside of.
These numbers right here. What numbers can I plug into that function? I can plug in all positive numbers, right? All negative numbers, 0, decimals, right? I don't have any problems plugging any numbers into this. The domain of this is all real numbers. Now, how do we say that? We can write it in interval notation as saying the domain is everything between negative infinity to infinity.
Do the double R thing.
Or you can do the double struck R like that. I like this because this is what we call interval notation, although this is perfectly fine, means the same thing. But I want to stick to some notation here. Interval notation's the standard. Sometimes you might see something like this. Have you ever seen this? X with this little e next to it, like X is an element of this. That just means that the X's that you pick can come from any number within this interval. So it's an element of this interval. Pick a number out of there, you're free to plug it in. Now, what about the range of this? The range is what comes out. So the domain are the ins, the range are the outs. 0 to infinity. Is it possible to get a negative number spit out the other side of that function? No, it's not possible, right? So I would say, if I said that f of x was y, because that's what the standard use, say y is an element of, you said from 0 to infinity? Now what about 0 itself? Can we get 0 out? We can, right? If we plug 0 in, it's going to spit 0 out. So what I do is I put a bracket on the 0, which means include 0. Now what's interesting about this is if you look at it this way, then if we actually try and graph this function, we all know what this looks like. The domain, right, says the x's can be anywhere on the number line. So that means I should be able to take any number here, right, and plug that into the function. And the outputs, the range, should only go from the y values that are from 0 up, right? And when we draw it, that's exactly what we get. We get this parabola like this, noticing that any point that we pick, right, the x values can be anywhere, but the y values have to be from 0 and up. All right, let's look at one other function before we move into sine. How about square root of x? Let's change it up a little bit. Do you have any problems there with the domain?
Can't put anything negative.
Can't put anything negative in there, can you? Because then it'll be an imaginary number, right? So can I put 0 in there? Square root of 0 is 0. So I can put 0 in there. Square root of 1, 1. Square root of 2 is, I don't know, square root of 2. But I could put 4 in here because I know the square root of that's 2. I could put, what, the next perfect square is probably 9. I'm just going to spit out 3. Now, I could put numbers in here, right, like 2, but those are decimals. And no negatives, though, right? So the domain of this is I can basically pick an x as long as it comes from, it's bigger than 0 or 0 itself, right? It can be 0. So I could say from 0 to infinity, that, greater than or equal to 0.